Okay, let's give this a shot. Library's a little noisy here, so hopefully it's not too bad. But we are onto a new section. So we're looking at the volumes by cylindrical shells, which is brand new. But let's just look at a question and see what that's even going to mean. So we want to find the volume of the solid obtained by rotating about the y-axis, the region bounded by y equals 2x squared minus x to the third, and y equals 0. To help me graph this, I initially kind of plotted where the zeros are going to be, so I know it's 0 and 2. So between 0 and 2, we have this little kind of hill shape there. So now if we're rotating around here, that's what we got. And think if we're going to set up our normal washers that we'd be working here with, we'd get something that's looking like that. The issue with this is think if we're doing our big R minus our little r, isn't this the same function for both? And it's like, oh, that is the same function for both. Well, maybe we can rewrite this, right? Like maybe we can kind of solve for x equals and things will be all good. And if you take this and think for a second, how do I solve this for x equals? Maybe you like factor out your x squared here. And there's no good way. This is just kind of sadness. We can't solve for x here. It's just not possible. So then all of a sudden we can't do this by the methods that we have at our disposal. So we need to think of something new, which is where this volume by cylindrical shells comes into play. This, I'm gonna jump over here, because I want us to rethink this problem quickly. So what shells are is, hopefully everyone's seen those like Russian nesting dolls. You know how it's like the little lady inside another lady inside another lady, and then eventually it's like a baby on the inside? That's kind of what we're working with here. If we make a little like cylinder here, that covers like this space. And then think, oh, we might need a little bit bigger cylinder for the space right after it. And we keep getting bigger and bigger, and we keep nesting these things. Right, these are all cylinders. So if we're looking at one of these cylinders, it's paper thin, literally like a piece of paper kind of rolled up into a cylinder. And we'd want to find kind of the area of this. So if we unfurl this thing, I think that's how you spell furl. It's just a big old rectangle. And if you think, well, how far is this top rectangle shape? That's a circle up here. So the distance for that, if we think, oh, what's the circumference of a circle? It's 2 pi r. And the height here is normally just h. But if you look at all these, the height is actually represented for each of these, like the dark green, the purple, and the light green. It's just the height of the function. So it's literally, what is our function here? And if you're thinking the radius, since we're just around the y-axis, the radius is just, what x value are you at? So we actually now have a nice formula to get this volume. And that's exactly what we have here. The volume of a solid formed by rotating about the y-axis, the region under the curve from f of x, is this formula. So we're from a to b, 2 pi. It's radius, but the radius here is technically just the x values, and the f of x here is just your height. And we add up an infinite number, and we should get what we're looking for. Let's go back to our question and see how that's going to relate to this. So if I redraw this quickly, we have that shape. Oh, and I'm going to botch this one, aren't I? And that shape. But now we're thinking we want to make shells out of this. So let's think of our integral here. So if we're integrating it's from 0 to 2, 2 pi. And then remember, we're thinking we want to know what the r is. So maybe I'll leave this up just so we can compare. We want to know what our r is, which in this case, it's just the radius, which is x. And our height of this function is just what is the function. So it's that one up here, 2x squared minus x to the third dx. Let's go through and solve this now. Hopefully I left myself room. The 2 pi can come out front. That's not really affecting us. We distribute in 2x to the third minus x to the fourth. Antiderivative. 1/2 x to the fourth minus 1/5 x to the fifth. From 0 to 2. 2 pi. This is going to be 8 minus 32/5, I believe, minus 0, of course, after all of that. And if we actually do the subtraction and do all this out, we're getting 16/5 pi. So, definitely different thought here. Take a second and process this. See how this one didn't quite work for us and we were in sadness state? Whereas this one, our shells worked. Let's try another example like this. So we want to find the volume of the solid obtained by rotating this about the y-axis. Notice what's different here compared to the questions we'd been doing. We spun around the y-axis, but now we were able to stay with respect to x. All the questions we'd done before were the opposite. So this can be confusing. And we've actually done this question normally. You can go and do this our preferred method. I want to show you that shells is going to get us the same answer here. So think if we're doing shells here, we're like, oh, okay. It's between 0 and 1, 2 pi. Since we're spinning around the y-axis, the radius is just x. And then we need the height of this function. The height of this function is a little different than here. Here, top minus bottom, we were subtracting 0. So it's just the function. Here, our top function is y equals x. And the bottom is y equals x squared. So we need x minus x squared. That is the height, right? This is our radius. That's our height. And we should be able to go through and solve this. Library is getting rowdy today. So we can go through and solve this. 1/3 x to the third minus 1/4 x to the fourth. 0 to 1, 2 pi there. 2 pi of 1/3 minus 1/4. So is that pi over 6? I didn't even check. Hopefully I didn't mess this one up. It is. Pi over 6 we should get by doing that. If you want to compare this answer to our other way, how we've been doing it, normally we'd have to shift this. Right, so maybe other way, let's do in purple. We have x equals y here and x equals the square root of y. So the old way we were doing this, we needed it with respect to y. And then we needed our big radius here, which is the square root of y squared. Right, our big r here would be the square root of y minus 0. And our little r would have been y minus 0. We square those, and you get the big R squared is y, little r squared is y squared. Hopefully it's the same thing. I didn't plan this one ahead, but it should be. If not, we're breaking math. Oops, sorry, that's from 0 to 1. 1/2 minus 1/3. Wow, same thing. Incredible how math works like that, huh? Okay, take your time and kind of see the difference between these different forms. All of our ones tonight we're going to be using the shells for. These are just called shells. So we have disc, washer, shells. The homework we're going to be looking at tomorrow, if you want to get a jump on it, is 6.3. 3 to 7. Okay, guys. I'll see everyone in class tomorrow. It's Friday. Bye.